Science is a process filled with trial and error, which means we don't always get it right the first time. In hindsight, some of the working theories in any scientific field, from biology to geology to chemistry to astronomy, might seem a little ridiculous, and some have definitely been more ridiculous than others. Here are 6 ways scientists radically misunderstood the world in their attempts to figure out how it works. Where do babies come from is an age-old question. For some animals, that answer was fairly obvious, but tiny creatures like worms, insects, or mussels, they obviously develop out of non-living matter, like mud, right? This idea of spontaneous generation was cross-cultural, from Babylon to China to good old ancient Greece. As our favorite science expert, Aristotle, wrote, some animals come from putrefying earth or vegetable matter, or other animals' organ secretions. He believed that some kind of vital heat existed in all matter that could create different kinds of life. Frothy bubbles were supposedly involved? I don't know. But spontaneous generation was accepted as fact by many scientists for over a millennium, like up through the 17th century. Luckily, there were others who thought it was nonsense and conducted experiments to prove it. In 1668, the Italian physician Francesco Redi set out to disprove the widely believed idea that maggots could spontaneously generate from meat. He used a series of jars. Some were left open, some were covered with gauze to keep flies from landing on the meat, and some were sealed completely. Unsurprisingly to us, no maggots were found in the sealed jars, and plenty of maggots were on the meat in the open jars. As for the gauze-covered jars, maggots were on the gauze and the meat, suggesting the flies had laid eggs on the gauze, but some had fallen through the small holes. Redi's experiments were the first major evidence against spontaneous generation. But there were counter-experiments. Some researchers claimed that colonies of microorganisms could generate from heat-sterilized solutions inside sealed tubes. Still, other scientists replicated those tests and got different results, concluding correctly that just a moment between sterilization and sealing the container was enough for new microbes to move in. One of those scientists was Louis Pasteur, of heating stuff to kill off microbes fame. In 1859, he ran a series of experiments with flasks that had specially curved necks to keep the insides from being contaminated. In each flask, he boiled beef broth for an hour to sterilize it. Then he broke the necks off some to let air in. The broth in those was cloudy, indicating microbes had found a home and were reproducing, but nothing grew inside the unbroken containers. After Pasteur's research, the idea of spontaneous generation went downhill. But hey, speaking of the many things Aristotle got wrong about the way the universe works, in addition to the 4 classical elements of earth, wind, fire, and water, there was ether, the stuff that filled the heavens. You can blame Plato for starting the idea, but his student, Aristotle, definitely expanded on it. Like, he specified that ether moved in circles, and crystal spheres of the stuff held the celestial bodies. That's how the planets and stars orbited. In Latin, ether was renamed quintessence, and was a big ingredient in alchemy-based medicines. But in the 17th and 18th centuries, the ether was reinvented to explain new scientific studies about light, specifically how it was able to move through space. After all, sound needs a medium to propagate, so surely light needed something too. To differentiate this more science-y ether from its classical predecessor, scientists at the time called it the luminiferous or light-bearing ether. Dutch physicist Christian Huygens believed that light was a wave and proposed it traveled through an omnipresent, perfectly elastic medium having zero density called ether. Meanwhile, Isaac Newton treated light only as a particle and used the ether to explain how light could refract or appear to change direction when it encounters a new medium. According to him, the ether was more dense around objects, so particles of light would scatter differently. Eventually, new experiments and ideas about light kept popping up, like that it's a transverse wave instead of a longitudinal wave like sound, and that it's a form of electromagnetic radiation. And those made the ether and its supposed properties more dubious. Ether had to be fluid, yet super rigid, and also massless. By the late 19th century, our equipment was generally sensitive enough that scientists could try to detect the ether, but over decades, no experiments found legitimate proof. The most famous of these was conducted in 1887, the Michelson-Morley experiment. Their goal was to detect the relative motion of the Earth as it moved through stationary ether, because that supposedly created an ether wind. And they would do that, hypothetically, by measuring the speeds of 2 light rays split from a single beam as they were bounced around by mirrors inside a machine. If they were even the slightest bit out of sync from one another when they hit a detector, because of ether wind speeding one up or slowing one down, they would create an interference pattern. So no interference pattern meant no ether wind, which is exactly what Michelson-Morley and even many scientists into the 21st century have found. Einstein also put a nail into the coffin of the luminiferous ether when he used special relativity to show that equations governing the electromagnetic force didn't need ether at all. But there are still a few people who think that the puzzle hasn't been solved, and assert that ether might be out there, and have some connection to dark energy or quantum field theory. Oxygen wasn't discovered until the 1770s, so early chemists had a different substance to explain how combustion worked. In 1669, German physician Johann Becher redefined the 4 classical elements into water and 3 different kinds of earth: terra lapidea, or stony earth, terra fluida, or liquid earth, and terra pinguis, or oily or fatty earth. According to him, wood was made up of ash and terra pinguis, and when it was burned, that oily earth was liberated, leaving the ash behind. In 1703, German chemist Georg Ernst Stahl renamed this element phlogiston and expanded on those ideas. Both burning and rusting meant a substance released phlogiston into the air, and plants eventually absorb it so the air doesn't combust. Meanwhile, combustion in a closed container stops because the air becomes saturated with phlogiston. But there were problems with this hypothesis, like some metals gained mass when they burned, even though they were supposed to have lost phlogiston. When the very flammable hydrogen gas was discovered as its own element in the 1760s, it was dubbed inflammable air, because, English is weird. Anyway, some natural philosophers thought that it might be pure phlogiston. Spoiler alert, it wasn't. The French chemist Antoine Lavoisier proved that hydrogen was its own thing by taking that inflammable air and dephlogisticated air, which was just oxygen, and heating them until they reacted and formed water. The work he did over the years showed that oxygen was the element responsible for combustion reactions, and phlogiston only existed on paper, but not in paper. That's mostly carbon. But Lavoisier couldn't completely figure things out. He dethroned phlogiston as the so-called substance of heat, only to replace it with igneous fluid, which got rebranded as caloric in 1787. As he explained it, conduction happens because caloric is attracted to matter. The less caloric a substance has, the more its atoms attract caloric fluid. Conduction is one of the 3 methods of heat transfer. For instance, imagine putting your hand on a hot frying pan. Don't, actually do it, but the thermal energy moves from the pan into your body. Nowadays, we know this happens because the higher temperature, and therefore more energetic, particles in the pan collide with the lower temperature particles in your hand, transferring some of their energy and heating you up. But 18th century scientists didn't know that. Lavoisier's ideas also covered why hot air expands. Caloric is absorbed into the air, which increases its volume. Plus, he was an important dude in chemistry, so the idea of caloric took off. The concepts behind it actually allowed one chemist to correct Newton's calculation of the speed of sound. But just like phlogiston, there were problems. People knew about conservation of mass, but somehow caloric had to be massless, yet occupy volume. Plus, it couldn't explain why water suddenly gets less dense when it becomes a solid, or how heat can propagate in a vacuum, as British physicist Count Rumford proved in 1795. Lavoisier himself acknowledged that his ideas about heat were just as valid as the mechanical model of the time, which related the heat of a substance to how fast its particles were moving. Eventually, both of these models were sort of smushed together and reworked into our modern understanding of how thermal energy works. Which is good, right? It shows that some of our scientific missteps aren't complete garbage. The steady-state hypothesis was introduced in the early 20th century, after astronomers learned the universe was not static, but expanding. Extrapolating backwards, that suggested that there was a moment of creation, that the universe didn't always exist. This model was nicknamed the Big Bang by the steady-state proponent and British astronomer Fred Hoyle to mock how ridiculous it sounded to him. Go figure. So instead, Hoyle and others doubled down on the idea that the universe looks exactly the same in every direction from every location and applied it to time as well. For that to be true, matter would have to be continually created to keep the universe's density from decreasing, which, I thought we had gotten past the idea of spontaneous generation, but there you go. But the steady-state model had one fairly big argument in favor of it. When astronomers first attempted to measure how fast the universe was expanding, and therefore determine its age under the Big Bang model, their data suggested the universe was only a couple billion years old. Scientists already knew the Earth was older than that, so either the Big Bang model couldn't be true, or the calculations were very, very off, and they were. That error was fixed by taking more accurate measurements, but the steady-state hypothesis had problems creep into it come the 50s and 60s. Observations of bright radio sources, like quasars and radio galaxies, were only being found at large distances from the Milky Way. According to the steady-state model, they should be distributed across all distances, but the data showed that the universe was clearly changing over time. For most cosmologists, the last straw came with the discovery of the cosmic microwave background radiation in 1964. That radiation wasn't predicted by the steady-state hypothesis, but it was by the Big Bang, and any attempts to use the steady-state model to explain its origin fell through. While the steady-state model was alive and well, it was used to support ideas a little closer to home, explaining the Earth's continents without knowing about tectonic plates. The contracting Earth theory was the main geodynamic model for about 2 centuries. It was formulated in the 1800s by American geologist James Dwight Dana and used a basic idea from planetary formation theory that a baby planet starts out molten and shrinks as it cools down and solidifies. While they obviously didn't have direct evidence of that back then, we can totally see the effect now on Mercury. By that reasoning, geologic features like mountains and valleys appeared because the Earth's surface cooled faster than the interior, like a grape shriveling up into a raisin. However, the discovery of heat produced by radioactive decay suggested that Earth's cooling rate was too slow and contraction was too small to make all those structures. And it couldn't explain the irregular distribution of Earth's features and why certain areas had way more earthquakes and volcanoes than others. Under a contracting Earth model, they should be randomly distributed around the globe. Other hypotheses were considered too, like the expanding Earth theory, which hit its peak at the turn of the 20th century. Italian geologist Roberto Mantovani published his hypothesis to explain continental drift, how the continents have been moving slowly over hundreds of millions of years. By his logic, in the past, Earth was so small it was covered by one continent, and then the planet swelled and oceans filled the gaps. His idea seemed kind of reasonable at the time, compared to the idea of tectonic plates sliding around the surface all willy-nilly. But the expanding Earth model struggled to explain how the Earth could grow so much. Some geologists piggybacked off the steady-state hypothesis and said new matter was constantly being generated inside the Earth. Others suggested there was a buildup of material from space. After all bodies in our solar system were formed by the collection of gas and dust, and stuff is constantly falling to Earth. But as scientists measured in 2011, the average change in the Earth's radius is a whopping 0.2 millimeters per year, or about the thickness of a human hair. Not exactly enough to explain how Africa and South America used to be joined. Really, it was scientists discovering evidence of seafloor spreading recorded in oceanic rocks that proved plate tectonics was the way to go. So science has come a long way, and thanks for coming along on this delve into history with us here on SciShow. If you want to learn more about other times scientists were wrong about new discoveries, check out our list show about pathological science. And for more about all kinds of research, you can go to youtube.com/scishow and subscribe.